Hey everyone. So we last time defined irreducibility and reducibility of polynomials when we're working with coefficients in an arbitrary integral domain. But now we're going to focus on the classical question, right, which was irreducibility over the rational numbers. Right? This is what mathematicians in the past, this is really what drove a lot of the study of ring theory, right? Is trying to understand how to factor polynomials over Q, right? Coefficients in Q. So we're going to start with this result. So this will be lemma 23.7. Let n be a natural number. And for, we're going to use little a. And z, let a bar equal a mod m. So we're going to use this notation a bit in this class, right? When you see a bar for an integer and we're working with a particular natural number, we're going to interpret that as just sort of shorthand for a mod m, so reducing mod m. And so here's the statement. So then the function phi from, so we're going to go from z bracket x to zm bracket x. Right, this given by phi of a0 plus a1x plus dot 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 plus a sub n x raised to the n equal to a0 bar plus a1 bar x plus dot 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 plus a sub n bar x to the n is a homomorphism. Right, so we're introducing this bar notation because here's one thing that we're going to want to do on a fairly regular basis is we're going to start off with a polynomial whose coefficients come from the integers, and then we're going to reduce the coefficients mod n. This lemma right here tells us that that's actually a homomorphism. It takes a polynomial with integer coefficients to a polynomial with coefficients in Zm. Okay, so to prove this, and it's really just, we just need to crank it out here. So, given a couple polynomials, so let's say f of x equal to a0 plus a1x plus dot 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 plus a sub n x to the n and g of x. That'll just have coefficients with b's, so b0 plus b1x plus dot 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 plus b sub k x to the k, both of these living in z bracket x. When we look at phi of f of x plus g of x, let's see what that means. Well, okay, so when we add the polynomials together, we'll get, I'm going to use sigma notation here. It'll be phi of sum ai plus bi times x to the I. And let's see, what does the polynomial tell us to do? Or, I mean, the function tell us to do? It tells us to reduce the coefficients of this polynomial mod m. So this is going to be sum ai plus bi x to the I. Now, here's the nice thing. We know that reduction mod n works nicely with addition right here. So this can be rewritten as sum AI bar plus BI bar times XI. And then we can split this up into two pieces, right? So this will be sum AI bar x to the I plus sum BI bar x to the I. And now what is this? Well, this is phi of f of x, and this is phi of g of x. Right? So this is phi of f of x plus phi of g of x, right? So this operation of reduction mod n on the coefficients respects the operation of addition. Now we need to check multiplication. I guess I'll do it here. Okay, so also, if I look at phi of f of x times g of x, that's going to equal phi of, so I'm going to multiply the polynomials inside the parentheses. That's going to give me sum I equal, well, I'm not going to worry about this, the index here, d sub I x to the I. And off here, just to remind you, so where di is equal to the sum n equals 0 to I, a sub I, no, sorry, a sub n, b I minus n. Right, so that's just the formula for coefficients when you multiply two polynomials. Now, what do we get here? So this is equal to, right, when I actually apply the homomorphism, that tells us that we'll get, or tells us to reduce our coefficients mod m, so I'm going to get di bar when I apply the homomorphism. Now, I want to just sort of off to the side think about what we have now. So if we bar di, what happens? So this is kind of scratch work. You can write it off to the side if you like. So di bar is equal to sum n equals 0 to I, a n b I minus n. And I need to bar the entire thing. And now we just need to think about, okay, when you reduce mod n, if you want, you can do all the operations and then reduce the final result mod n, or m, or you can, what's the other option? So this is saying do the operations and reduce mod m, or you can reduce everything mod m first and then do the operations. In other words, this is equal to sum n equals 0 to I, a n bar, b I minus n bar. Right? So, I don't want to write that. Yeah, okay, so what does that tell us then? That this is equal to the sum AI bar x to the I times sum bi bar x to the I, right? If you multiply these two polynomials together, what would you do? You would use, or you'd get coefficients who follow exactly that summation right there. And then who do we have? Well, this is phi of f of x, and this is phi of g of x, right? So the key to this is just recognizing that reducing mod m behaves nicely when it comes to our standard arithmetic operations, both addition and multiplication, right? The key was really right there, that these two things are equal. Okay. So this is sort of a technical result that we're going to use quite a bit. This is going to be one of our techniques that we're going to use when studying reducibility and irreducibility of polynomials. Right? If you have a polynomial with coefficients in the integers, you can reduce it mod m and everything behaves nicely. And you might notice, I wrote up at the beginning there, the heading was irreducibility over Q, but then the lemma had something to do with polynomials whose coefficients are in Z. We're going to find out that that's actually a nice, that we will be able to work with polynomials over Z to understand factorization with polynomials over Q. So our next definition here, so let's let f of x equal a0 plus a1x plus dot 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 plus a, what do I need here? A sub n, x to the n, be a polynomial in Z bracket x, where I want this to be an honest degree n polynomial, so we'll just say where a sub n not equal to 0. The other ones can be 0, that doesn't matter. The content of f of x is the GCD of the coefficients, a0, a1, up through a sub n. Now, if the GCD of a0, a1, up through a sub n is equal to 1, then we say that the polynomial is primitive. So then f of x is primitive, right? So if you have a polynomial, you can look at take all the non-zero coefficients, find the GCD. That number is called the content. In the case that the GCD is equal to 1, when the coefficients of your polynomial are relatively prime, then we say that you've got a primitive polynomial. So for example, 2 plus 3x plus 4x squared is primitive. But if we look at 2 plus 2x plus 4x squared, this one is not. Okay, and now this leads to our next theorem. This is theorem 23.8. And this theorem has a name. It's called Gauss's lemma. And so what we need are a couple of polynomials. So let's let f of x and g of x be polynomials with integer coefficients. If f of x and g of x are primitive, then so is their product. So so then f of x times g of x is primitive. So what this theorem says is the product of primitive polynomials is primitive. And the proof is pretty slick, so pay attention and have fun with this one. Okay, so what we're going to do is we'll go by contradiction. So we're going to assume that the two polynomials are primitive, but that the product is not. So suppose f of x and g of x are primitive, but f of x times g of x is not primitive. So what does that mean? That means that if you take the product and look at the coefficients, right, there is some divisor greater than 1, a common divisor of all of the coefficients, which means that there's some prime common divisor. So it doesn't matter who it is. So let's choose a prime divisor of the content of f of x times g of x. Just choose any prime divisor, it doesn't matter. And now what we want to consider, so let's consider the homomorphism phi from z. Oh, and you know what? I need to call it p. Sorry, choose a prime divisor of the content of choose a prime divisor. I should insert it right there. Choose a prime divisor p of the content of f of x times g of x, and consider the homomorphism. Now we're going to go from z bracket x to zp bracket x, and it's exactly the homomorphism that we had last time. So let's just say of lemma 23.7. In other words, what we're going to do is we're going to take the coefficients of any polynomial here and reduce them mod p. Now, what we know is that this prime divisor of the content, it divides every coefficient of f of x times g of x. Right? So since p divides each coefficient of p f of x times g of x, we have well, let's write it like this. So we have phi of f of x times phi of g of x equal to phi of f of x g of x. Now, since p divides every coefficient of this guy, when you reduce all the coefficients mod p, what do you get? You get 0, right? So we get the 0 polynomial. Now, ZP is a field, which means it's an integral domain, which means that ZP bracket X is an integral domain. So what we have now, think about this is something in ZP bracket X, so is this. Each of these is an integral domain. We don't have 0 divisors. That means that one of these two has to be equal to 0. So since ZP bracket X is an integral domain, phi of f of x has to equal 0, or phi of g of x has to equal 0. So what does that mean? It means, so for example, if phi of f of x equals 0, that means that p divides every coefficient of f of x. If this one's 0, then p divides every coefficient of g of x. So this implies that p divides every coefficient of f of x, or every coefficient of g of x. So what does that mean? That means that either f of x is not primitive or g of x is not primitive. So f of x or g of x is not primitive. That's a contradiction. All right, so that completes the proof. So what do we know? If you start off with two primitive polynomials, then the product has to be primitive. I just love this proof. It's just really slick. It just makes use of the homomorphism property right here. It makes use of the fact that we went to a field, and there was a reason we chose a prime divisor, because we wanted the coefficients to be a field, which would guarantee that we have an integral domain here, which means that I could conclude that one of these two had to be 0. All right, so I think that's fun. I like that proof. Okay, this next result that we have is really the key to the study of factoring polynomials over the integers, right? So let's say it like this. So the next result is key to the study of reducibility, or really irreducibility, I guess we should say. Irreducibility over Q. And I kind of hinted at this a little bit, so let's get the statement of the theorem. So this is theorem 23.9. So if we have some polynomial, so if the polynomial f of x in z bracket x, so we have some polynomial with integer coefficients, if this polynomial is reducible over Q, then f of x is reducible over z. This theorem, when you first look at it, you say, this seems impossible. Right? It's hard to believe. So you take a polynomial, yeah, it's got integer coefficients. Now suppose you do some work and you figure out how to factor it over the rational numbers, which means that you allow rational coefficients all over the place. It turns out that if you would have worked a little bit harder, you could have factored that polynomial where you used integer coefficients all the way. Right? So when I first look at this theorem, I say, no way. And this is the kind of thing that when you first see it, it seems amazing. And then once you see the proof, you say, oh, yeah, of course this is true. So what are we going to do? What we're going to do is say, assume that we factored over Q, and we're going to use that factorization. We're going to manipulate it a little bit and find a factorization that just requires integers. All right, so let's assume that f of x equals g of x times h of x. So suppose we can factor it, and now we're going to allow g of x and h of x to live in Q bracket x. And we want this to be an honest factorization, which means that the degrees of both g and h have to be strictly less than the degree of f. So assume this, where g of x and h of x are in Q bracket x, and the degree of g of x and the degree of h of x are strictly less than the degree of f of x. So we have an honest factorization of our polynomial. Now, one thing we can note, so let's say first, note that we can assume that f of x is primitive. And here's the reason. Let's say that all the coefficients of f of x were, divisible by 2, for example. Well, then you could divide both sides by 2. That's not going to screw anything up here because we're just using rational numbers on this side, so that's not going to screw anything else up. And this polynomial will remain, if it had content that was divisible by 2, then this would remain a polynomial with coefficients in the integers. Right? So we can assume that it's primitive. So otherwise, just divide by the content of f of x. Right, so let's just assume it's primitive so that we don't have that floating around. And so now, introduce some notation here. So now let's let little a is going to be the least common multiple. So this is going to be the least common multiple of the denominators of g of x, and b be the LCM of denominators of h of x. Okay, so now what I want to do is I'm going to multiply both sides of this equation by a times b. Essentially, we're going to clear the denominators out. Right, so then we have a b f of x is equal to, and I want to write it this way, a times g of x times b times h of x. And notice here, and in fact, let's point this out. We'll say, and note, what we did is now we've cleared out the denominators of g of x. This polynomial right here lives in z bracket x. This one also lives in g bracket x. So we'll say, and note that a times g of x and b times h of x are in z bracket x. So, all right, well, okay, if they're in, if they live in z bracket x, then we can talk about the content. So let's let, I'm going to call them a hat and b hat. So let's let a hat be the content of a g of x, and let b hat be the content of b times h of x. So then, we can write a times g of x equal to, let's say a hat g hat of x, and b h of x is equal to b hat h hat of x, where, what am I doing here? Let's finish the sentence here. So where g hat of x and h hat of x are primitive. So what do we have here? Well, okay, so here's some polynomial, it's got some content. Here's some polynomial, it's got some content. When you pull the content out, what you have is constant times a primitive polynomial. So that's all I've done right here. This has some content, pull the content out, and now you have constant, right, times primitive polynomial. Same thing here. So all we've done is factor the content out of a g of x and b h of x. So it follows that where do I write it? Yep. A b f of x is equal to, so let's see, AB f of x is equal to this, but I'm going to replace each of these with their hatted versions. And so this is equal to a hat g of x, g hat of x times b hat h hat of x. Now, since f of x is primitive, right? We assumed it was primitive. This a times b is the content of f of x. All right, so since and I should really let me extend this. This is a hat b hat g hat of x h hat of x. So since f of x is primitive, the content of AB f of x is AB. Now also, since g hat of x times h hat of x is primitive because h of these is primitive, apply Gauss's lemma. So since g hat x h hat of x is primitive, there's Gauss. The content of g hat of x, h hat of x is a hat times b hat. So now what are we looking at? We've got primitive polynomial, or constant times primitive polynomial, constant times primitive polynomial. What does that force us to conclude then? It forces us to conclude that AB is equal to a hat b hat. So it follows that AB is exactly equal to a hat b hat. And so what does that mean then? That allows us to conclude when I divide both sides by AB, we get f of x is equal to g hat of x times h hat of x. So therefore, f of x is equal to g hat of x times h hat of x. That's exactly what we needed, right? We started off with factorization over q, and then what we end up with? We ended up with f of x equal to polynomial in z bracket x times polynomial in z bracket x. One thing to note, right, so just if you follow the proof, right, what this proof involved, all it really did, once you read it, all it involves is just sliding constants around. That's all that happened. So note, in the proof, all operations involves sliding constants. And when you slide constants around, it doesn't change the degrees of the component polynomials. In other words, the degree of g of x matches the degree of g hat, same with h hat, or h and h hat. So we can say, and so the degree of g of x equals the degree of g hat of x, and the degree of h of x equals the degree of h hat of x. And let's just finish off with an example. So here's my example. So let's look at f of x. That's going to be 6x squared plus x minus 2. And let's just say that I was, messing around here and I realized, right, I was able to factor it over q. And so the factorization is going to be 3x minus 3 halves divided by 2x plus 4/3, right? So here's a factorization of my polynomial f of x, right? But it's happening over q, right? This is my g of x here, and this is my h of x, right? But I wasn't smart enough to factor this polynomial over z. All I could do is figure out how to factor it over q. So let's see, what do? We find the least common multiples of the component polynomials and multiply both sides. So let's see, the least common multiple here, that was the thing I called a, that is going to be 2. And then the least common multiple here, b, is going to be 3. So remember, now we multiply both sides by the product of the least common multiples. So I'm going to have 6 times 6x squared plus x minus 2 equals, and then let's see if I want to do it separately. Yeah, so I'm going to do it, multiply this one by 2. So a times g of x is going to be 6x minus 3. And b times h of x, that's going to be 6x plus 4. Then what do? We pull out the content of each piece. So this will be, the content here is going to be 3. So this will be a 3 times 2x minus 1. The content here is going to be a 2. So that'll be 2 times 3x plus 2. Now divide both sides by 6. And so what we get is 6x squared plus x minus 2 is equal to 2x minus 1 times 3x plus 2. So when you see it, notice what happened. I mean, we multiplied both sides by 6 and then just slid things around a little bit and made sure that we had, what did I do? Yeah, I multiplied by least common multiples, pulled contents out, divided, and there we have it. Right? So really nothing that earth-shattering when it's done. But this is a nice result, right? And what this allows us to do when we want to talk about factoring polynomials over q, we can convert to, or we can what's the right word? It allows us to consider factorization over z instead. Okay, so that's a good place to stop. We will see you next time.